Alright, the continuing vector story. Previously we explored how to work with vectors that are just floating around in space. We looked at the language of vectors and what magnitude and direction and sense and how to communicate all those using geometric form and using algebraic language as well. Now we're going to sort of transform a little bit or improve perhaps the way we talk about vectors by using our coordinate system as a way of organizing some of the work and maybe making it a little easier. And to give you an example of this, we have a problem that was from the previous packet somewhere. I can't find it, but either way, the problem here has two vectors, A at 20-degree angle from horizontal, and it's 20 kilometers long, and the vector BC is 19 kilometers long, and it's going due north. The objective is to calculate the length of the sum of those two vectors. That would be, in other words, the magnitude of vector AC. Now, using the skills that we learned in trigonometry, we would use the cosine rule, or law of cosines, and ascertain 31.95 is the length of vector AC. However, if we look at the picture and center point A as the origin on an XY grid, so here's the X grid, here's the Y grid, here's the origin, then we could actually find the length of AC by using the two legs of a right triangle. So, given the 20-degree angle and the 20-kilometer hypotenuse, if we just use the sine to find the length of Y, add that to 19, we have one leg of the right triangle, and we use the cosine to find the length of x. That will be the other leg of that triangle. And the Pythagorean theorem, a little bit more easy to use, gives us the exact same result. So what we learn from this particular comparison is that it's somehow easier to work with vectors if we use a coordinate system. Therefore, we can work with horizontal and vertical vector components. So that's the impetus for this sort of improved vector work. It's vectors in the coordinate system. It starts off with this idea that we can take a unit vector, a vector that is 1 unit long, and make it horizontal, and we'll call that vector I. That will be the horizontal unit vector. And here's vector J, the vertical unit vector. If we add any scalar multiples of horizontal and vertical vectors, we can get to any point on the coordinate plane. So for example, here A could represent the number 3, so this would be 3 times the horizontal unit vector, and then this could be 2 times the vertical unit vector, gives us this vector right here, essentially the result of going over 3 and up 2. That makes it easier to find the magnitude of this particular vector, and it also makes it possible to find the angle or direction by using our basic trigonometry. So, to put that into clearer perspective, we'll take a look at this particular applet. Here we have just a vector, and this vector could be anywhere in space, but what we're going to do is choose to locate it at the origin. Essentially, we can describe or define this particular vector as the sum of horizontal and vertical parts. And we've seen that when you add two vectors together, you get the resulting sum vector, the resultant vector. But we now have a horizontal component and a vertical component. Now, if we put a grid on this, now all of a sudden I can see that I went over 15 and up 20. And if you recognize that as a 3, 4, 5 right triangle, this should be 25 units long. And here it says the magnitude of the resultant vector is 25. So now all of a sudden any vector that we describe, it can be described by looking at its horizontal and vertical components. That enables us then to ascertain the magnitude much more simply, and it enables us to find the direction or the angle that the vector is being launched as well. So that's basically what this whole rest of the first packet is about, is getting comfortable with adding and subtracting and multiplying scalars of vectors using the coordinate plane. So a very simple example is looking at adding two vectors, v and w, where v is 4I minus 3j. And so what that means is 4 horizontal vectors over horizontal unit vectors and 3 vertical unit vectors down. So this is the vector v right here. And we are going to add vector w, which is 7 horizontal unit vectors and 5 vertical unit vectors up. So we go over 7, we go up 5. The blue represents vector w. When I add them together, you can see we could take vector v, relocate it over here, and it shows the resultant vector, which appears to be almost horizontal. To add the two, all I have to do is recognize that I am adding 4 horizontals and an additional 7 horizontal parts. So that's a total of 11 horizontals, and 11 turns out to be the part of the resultant sum vector. And then I have to go down 3 verticals, up 5 verticals, with a net gain of 2 verticals up. So collecting like terms, essentially, we end up with 11I plus 2j. Now this notation, in my opinion, tends to be cumbersome. All the i's and j's tend to be just placeholders. So there's an alternative notation. It's called matrix notation, and I prefer this, and you'll see this a lot more from IB. But we arrange the vertical and horizontal in an array. The vertical is down here, and the horizontal is up there. So this is 4 horizontal, down 3 vertical. You can see then that that enables us to, when we add our components, we can add 4 and 7 across, and we could add -3 and 5 across, and we get the resulting 11 too. But just remember, we have the algebraic notation representing the sum of the vectors, and then we also have the geometric. Obviously, it's important that both are represented when we do our work so that we can verify and cross-reference. In your packet, you'll see several different examples illustrated and highlighted of ways that we can add and subtract vectors, and some language that you need to look at. What you need to do is study these packet of materials as you were asked to, if you haven't already. I will mention one more thing here before I close, and that is the 3D. We work with 3-dimensional vectors. All we do is add a third dimension, literally. Notice in the graph, you'll see different 3D graphs, but I like them where the x is still the horizontal axis. And what we're going to do is take the vertical axis and rotate it down to the ground. So that would be the y-axis. X and y then would represent, so for example, the surface. And then we can take a z-axis, which will take us up and down through space. But when we do our work to find 3D vectors, all we do is just what we did before. We group and add the vertical and horizontal and depth components together. All of the mathematics you'll find is exactly the same. And you'll see examples of this in the text, and you'll see opportunities to work with 2D and 3D vectors in the packet of materials that I gave you. So be diligent, do some of this work. Next week sometime I'll add some videos on applications of vector work and some dot product stuff. And hopefully you'll be at least familiar with this to some extent when we start the school year. So hope summer's going great. Signing off.